Hi folks, in our last video we talked about the second law of thermodynamics and entropy. In this video we're going to take it one step further, introducing Gibbs energy and show how that relates to the second law. So let's start with the Gibbs energy itself and its definition. If you recall from our video on the introduction of entropy, we talked about the Clausius inequality, which says that the entropy change for the system, in this case we have it in differential terms, is greater than or equal to the heat change or the heat transfer for the process regardless of whether it's reversible or not, divided by T. Of course, if you'll remember the definition of entropy, if we have a reversible process, that entropy change is equal to dq over T. So based on this, and without going through the derivation, we have defined a new function of state called the Gibbs energy, which is represented by G, as you know, as being equal to H enthalpy minus the product of temperature in kelvins and the entropy. Now, it is important to note that, of course, we are defining it this way. This is the reason for, of course, the 3 bars instead of a normal equal sign. So this is the definition of the Gibbs energy. And again, this comes from a derivation based on the Clausius inequality, which again we're not going to go into. Now, through that we can see that, for example, if we remember the definition of enthalpy being related to the internal energy plus the pressure volume product, we can run through again a derivation of just a few steps, and we're not going to go through that here, to show that we end up with this particular inequality representing the Gibbs energy being less than or equal to this particular summation. Now this is actually fairly important because, again, the Clausius inequality is based on the second law of thermodynamics, and using the Clausius inequality to derive this means that this inequality that we have here, this expression of dg less than or equal to this set of terms on the right side, is an alternative expression of the second law of thermodynamics. Now, why is this important? Well, if we've got a situation where we have a constant pressure process, which is isobaric, then this last term, which is volume times dP, because it's isobaric, meaning the pressure does not change, that means that the dP term goes to 0, and that term in the inequality disappears. And then if it's isothermal, the first term also disappears because there's no change in temperature. So under those conditions, we can see that dg is less than or equal to dW. Now here, this dW refers to non-expansion work. Okay? And you may, of course, ask the question, what do we mean by non-expansion work? Well, expansion work is the work that would occur when a process is expanding or compressing. When a substance undergoes expansion, it has to push back its surroundings, and that means it is going to be doing work. That's what we mean by expansion work. And that, of course, is most important when dealing with gases, and as we talked about in a previous video, an example of that would be simply the expansion of gasoline vapor that occurs in your car when it is ignited, and the work that it does, which causes your car to move forward. So non-expansion work is work that is not that kind of work, and some examples of that, there are many examples of work that are non-expansion, but one of the most important in the case of our particular interests would be electrical work. When we talk about electrical work, the work associated with the flow of charge which is important in biochemical systems. That's an example of non-expansion work. So we have a situation here where, and this can actually be important, it's something that we're going to discuss later on, but in the case of a situation where we calculate delta G, then the delta G is equal to the maximum non-expansion work. And I have to remind you that according to sign convention, remember when W is less than 0, that means the system is doing work. So when delta G is negative, it's going to give us the maximum, the absolute value of delta G is going to be the maximum work we can expect from our system. And again, we'll talk about that a little bit later on. Now, if we have no non-expansion work in our system, then we have the inequality that, of course, dg is less than or equal to 0, and of course this is one you've certainly used before and seen before, that in a situation where we have isothermal and isobaric process with no non-expansion work, then calculating delta G and finding it being less than 0 means that the process will occur spontaneously. And again, this is due to the fact that we have the situation where we've derived this based on the second law of thermodynamics. So delta G being less than 0 is an indication of spontaneity under conditions, again, I can't emphasize this enough, of constant temperature and constant pressure. So let's talk about an isothermal process and what delta G would be equal to for that. We know that since the Gibbs energy is defined as being H minus T times S, that delta G is going to be equal to delta H minus delta TS, and it's important to note that delta TS means it's the difference in the temperature entropy product, so it would be the temperature, final temperature times the final entropy minus the initial temperature times the initial entropy, and that would be correct under all circumstances based on the definition. But if the process is isothermal, being constant temperature, then this reduces to the more familiar expression that you have no doubt used before, that delta G is equal to delta H minus T delta S. So, and again, for most of the circumstances and the situations that we'll be discussing, this is the expression we will use when determining delta G for a particular process. All right, so one last caution here when dealing with these calculations, and that is standard conditions. Standard conditions, of course, as we mentioned before, being conditions under which we have 1 bar pressure. Now, it is important that you note that when you look values up in the back of the book of, say, the Gibbs energy of formation, delta G sub F, that those values that are tabulated are the standard for standard conditions. All right, remember that superscript there means that we're talking about standard conditions, and so they really only apply to standard conditions. When we talk about delta G under standard conditions, then of course our equation that we discussed on the previous slide becomes delta G naught is equal to delta H naught minus T times delta S naught. So you can certainly look up the Gibbs energies of formation in the back of the text to determine, for example, delta G for a chemical reaction. Delta G naught for the reaction, of course, being the product, some of the delta G's of formation of the products minus the delta G's of formation of the reactants. So again, if we use those values from the tables, we're going to get delta G naught for the reaction. Now the question would be then, once we've calculated that, and if we find delta G naught for the reaction is less than 0, does that mean it's spontaneous and that reaction is spontaneous and going from reactants to products? And the answer is no. And we'll talk about this in a little bit more detail later on when we talk about equilibria. But the issue here is that it's not necessarily spontaneous, because the delta G naught that we would have calculated here would be based on all of the substances, the reactants and the products, being at standard conditions. If they're not all at standard conditions, then this will not give us delta G for the process. And there is a difference between delta G and delta G naught. Again, delta G naught refers to standard conditions. When we use tabulated values, we're calculating delta G naught for standard conditions. The spontaneity process only refers to, or using delta G naught being less than 0 as an indication of spontaneity, would only be correct if all of the products and all of the reactants were under standard conditions. So we have to be careful about our interpretation of the sign of delta G naught. And we'll come back to that in future videos when we talk about delta G naught as it applies more specifically to reactions and equilibria. So this ends our brief discussion introduction to the Gibbs Energy. We will continue with our discussion of the applications of the Gibbs Energy in future videos, but in the meantime, have a good time. Goodbye.